Hello my friends and welcome back to the You Can Do TV channel. In this section, You Can Do TV channel will take you to visit leading wind turbine factories to explore the wind turbine manufacturing process. Here, against the backdrop of the sea breeze and the distant hum of wind turbines, engineers, technicians, and craftsmen collaborate to produce some of the most advanced wind turbines in the world. The production process at HERE is a carefully orchestrated symphony of precision and innovation, designed to create turbines that are not only efficient and reliable but also environmentally sustainable. It all begins with the arrival of raw materials at the facility, where massive shipments of steel, concrete, carbon fiber, and other essential components are carefully unloaded and inspected. Once the materials are deemed suitable for production, they are transported to various workshops within the facility, each dedicated to a specific aspect of turbine construction. In the tower fabrication workshop, skilled welders and metalworkers meticulously shape and assemble the towering structures that will support the turbines high above the ground. Using state-of-the-art machinery and techniques, they weld together massive steel sections to create the sturdy framework upon which the turbine will be built. Meanwhile, in the nacelle assembly area, technicians focus on piecing together the intricate components that make up the turbine's power generation system. This includes the generator, gearbox, hydraulic systems, and control electronics, all of which must be meticulously aligned and integrated to ensure smooth and efficient operation. But perhaps the most fascinating aspect of the production process lies in the creation of the rotor blades, the aerodynamic marvels that capture the wind's energy and convert it into electricity. In a dedicated composites workshop, skilled craftsmen and women work with advanced materials such as carbon fiber and epoxy resin to create blades that are not only lightweight and durable but also highly efficient. The process begins with the fabrication of a mold, which serves as the template for the blade's shape. Layers of carbon fiber composite material are then carefully laid down and infused with resin, creating a strong and flexible structure that can withstand the forces exerted by the wind. Once the blade is formed, it undergoes a series of finishing processes, including sanding, painting, and quality control inspections, to ensure it meets Nordex's exacting standards. Throughout the production process, quality control is paramount. Nordex employs a team of inspectors and engineers who carefully monitor each step of the process, from raw material procurement to final assembly, to ensure that every turbine meets the company's rigorous quality standards. This includes testing components for defects, verifying dimensions and tolerances, and conducting performance tests to ensure reliability and efficiency. In the realm of renewable energy, wind turbines stand tall as icons of sustainability and progress. At the heart of these towering structures lies a complex assembly of modern machinery and equipment, essential for their production and assembly. These technological marvels not only facilitate the manufacturing process but also ensure the efficiency, reliability, and safety of the final product. One of the pivotal components in wind turbine production is the web floor stations. These stations serve as the nerve center of the assembly process, offering lift-up capabilities, secure transport mechanisms, precise positioning, and torsion-free manipulation of components. With the ability to handle heavy loads and intricate parts, web floor stations streamline the assembly process, reducing production time and enhancing overall quality. By providing a stable and controlled environment, these stations minimize the risk of errors and ensure consistent output, crucial for meeting the growing demand for renewable energy solutions. Furthermore, the low-turn hinge system plays a crucial role in the production of wind turbine blades. These systems enable efficient handling and manipulation of the colossal blades, allowing for seamless integration into the turbine structure. By minimizing torsion and ensuring precise positioning, low-turn hinge systems ensure optimal performance and longevity of the blades, even in harsh wind conditions. This innovative technology not only enhances the structural integrity of the turbine but also contributes to its overall efficiency, maximizing energy production and minimizing maintenance requirements. In addition to these key components, various other modern machinery and equipment play integral roles in wind turbine production and assembly. Advanced robotics and automation systems streamline manufacturing processes, improving efficiency and precision while reducing labor costs. Cutting-edge materials and manufacturing techniques enhance the durability and performance of turbine components, extending their operational lifespan and reducing maintenance needs. Moreover, sophisticated monitoring and quality control systems ensure compliance with stringent safety and performance standards, guaranteeing the reliability and effectiveness of wind turbines in harnessing renewable energy. The importance of modern machinery and equipment in wind turbine production and assembly cannot be overstated. These technological innovations not only drive efficiency and productivity but also underpin the sustainability and viability of wind energy as a renewable power source. By continually pushing the boundaries of engineering and innovation, the renewable energy industry can further accelerate the transition towards a cleaner, greener future. As we harness the power of wind with ever-increasing efficiency and sophistication, we pave the way towards a more sustainable and resilient energy landscape for generations to come. With ambitious plans for this unique series, Fraunhofer embarks on a journey to construct these rotor blades with meticulous attention to detail. Deliberate errors are introduced during the manufacturing process, with the anticipation of uncovering valuable insights later on. The production process begins with the assembly of the rotor blade shell, meticulously crafted from layers of glass, meticulously arranged from exterior to interior. Following the completion of the glass structure, a prefabricated belt is precisely positioned to serve as the backbone of the rotor blade. Next, the process transitions to fully automated vacuum infusion, employing a sophisticated mixing machine to saturate the fibers with liquid resin. Under the vacuum foil, the resin permeates the space between the fibers, ensuring a strong bond. This infusion process is closely monitored and evaluated using thermal imaging technology to gauge resin distribution and curing. Subsequently, a specialized two-component adhesive is applied using a semi-automated nozzle, ensuring precise placement along the seams. The rotor blade components are securely bonded together, held in place until the adhesive sets, providing stability against temperature fluctuations. Engineers conduct comprehensive investigations, testing rotor blade materials directly in the production environment. This real-world testing provides invaluable insights that cannot be replicated in a laboratory setting, guiding decisions regarding material suitability for series production. As the world's longest wind turbine blade, the LM88.4P, faced its inaugural static test, the tension in the control room was palpable. It is the colossal blade, stretching close to 90 meters, bore the weight equivalent to approximately 16 African elephants. Carefully planned and meticulously designed, the test aimed not to overwhelm the blade, but to simulate 25 years of rigorous offshore operation. Every detail was scrutinized, ensuring the load was applied in precisely the right manner to gauge the blade's resilience. The magnitude of the forces at play was staggering. Wind, akin to a storm with speeds reaching up to 100 kilometers per hour and rotor velocities of 280 kilometers per hour, would subject the blade to immense stresses. This test pushed the boundaries of what had ever been attempted before, necessitating the scaling up of equipment and the revision of standard procedures. But this wasn't the only trial. Fatigue testing, simulating millions of cycles of operation, was crucial to ensure the blade's longevity over its intended lifespan. The engineers meticulously monitored every aspect, striving to validate the blade's endurance under the harshest conditions. Transporting one of the world's largest rotor blades, a staggering 75 meters in length, is a logistical endeavor of epic proportions. Each blade, weighing in at 25 tons, requires careful planning and execution at every step of the journey. The process begins with loading the rotor blades onto specialized trucks. These trucks are equipped with custom-built trailers designed to support the immense weight and dimensions of the blades. As the convoy sets off, it attracts attention from bystanders and motorists alike, as the sight of such enormous structures navigating through narrow roads is truly remarkable. One of the most challenging aspects of transportation is navigating bends and curves along the route. Due to their length, the rotor blades cannot negotiate sharp turns without risking damage to both the blades and surrounding infrastructure. Therefore, meticulous route planning is essential, often involving the use of advanced mapping technologies to identify the most suitable paths with minimal obstacles. In some cases, road infrastructure may need to be temporarily modified to accommodate the passage of the rotor blades. This could involve removing obstacles, such as street signs or traffic lights, or even reinforcing bridges to ensure they can bear the weight of the convoy. As the convoy progresses along its route, it is accompanied by a team of experienced drivers and support personnel. Specialized equipment, such as escort vehicles and cranes, may be deployed to assist with navigation and handling at critical junctures. Throughout the journey, safety remains paramount, with measures in place to minimize the risk of accidents or damage to the blades. With careful planning, coordination, and expertise, the world's largest rotor blades reach their destination intact, ready to be assembled into cutting-edge wind turbines that will help power the future. The construction process of a foundation for an onshore wind turbine is a critical stage in the installation of wind energy infrastructure. A robust foundation is essential to ensure the stability and longevity of the turbine, especially in areas with varying soil conditions and weather patterns. Here's an overview of the construction process. Once the design is finalized, excavation begins at the designated locations for the foundation. The depth and diameter of the excavation vary depending on the foundation type and soil conditions. Careful excavation ensures that the foundation will be securely anchored to the ground. For reinforced concrete foundations, steel reinforcement bars, rebar, are placed within the excavated area according to the engineering specifications. Rebar provides tensile strength to the concrete and helps distribute loads evenly. After the reinforcement is in place, concrete is poured into the excavation. The concrete mixture is formulated to meet the strength requirements specified by the engineers. Special attention is paid to ensure proper compaction and consolidation of the concrete to eliminate voids and achieve structural integrity. Once the concrete is poured, it undergoes a curing process to attain its full strength. Curing may involve covering the foundation with wet blankets or using curing compounds to maintain moisture and temperature conditions conducive to concrete hydration. After the concrete has cured sufficiently, finishing touches are applied. This may include surface leveling, smoothing, and any necessary adjustments to ensure the foundation meets dimensional and quality standards. Throughout the construction process, quality assurance measures are implemented to verify compliance with design specifications and industry standards. This may involve inspections, testing of materials, and documentation of construction activities. Once the foundation is complete and inspected, the wind turbine components can be installed on top of it, including the tower, nacelle, and rotor blades. Lagerwey's wind power technology represents a leap forward in the field, exemplified by their recent wind farm developments in Finland, boasting a total capacity of 27.5 megawatts. At the heart innovation is the unique direct drive generator, heralding a new era in generator design. This groundbreaking technology offers a combination of low maintenance requirements, high efficiency, and natural cooling. The direct drive generator stands out for its simplicity and robustness, featuring a low number of moving parts that enhance its reliability and availability. Its high efficiency allows power generation even at wind speeds as low as 2 meters per second, maximizing energy output across various conditions. Moreover, the generator's design facilitates natural cooling through airflow around the turbine, further optimizing performance while minimizing heat production. In addition to the advanced generator, the wind turbines boast other impressive features. The compact yet spacious nacelle design ensures easy access for maintenance teams, while the strategic placement of the main controller within the nacelle facilitates convenient monitoring and data access. Furthermore, adherence to stringent lightning protection guidelines, including an extra shield in the nacelle cover, safeguards the electrical equipment against potential damage. Their solutions, such as the modular steel tower, MST, reduce transport costs and enable the construction of taller towers without the need for significant infrastructure adjustments. Additionally, the company prioritizes foundation optimization based on thorough ground penetration analysis for each project, ensuring stability and longevity. The transportation process of wind turbine blades, particularly those produced by LM Wind Power, involves a meticulous orchestration of engineering, logistics, and risk management. These blades, essential components of wind turbines, play a crucial role in harnessing wind energy efficiently. The journey of these blades from manufacturing to installation is a testament to the dedication and innovation of the teams involved. The company has established itself as a leading manufacturer of wind turbine blades, with a track record spanning over 4 decades and more than 130,000 blades produced. Their focus on reducing the cost of energy for customers has led to groundbreaking advancements in blade design and manufacturing processes. One of the key strategies is the optimization of blade length. Longer blades, such as the LM61.5P2, can significantly increase the annual energy yield of a wind turbine, sometimes by as much as 10% over a 20-year period. However, transporting these massive blades presents unique challenges. Each blade, measuring a staggering 61.5 meters in length and weighing around 150 tons, requires careful handling and transportation. To minimize the load on the turbine and optimize weight distribution, the company employs innovative techniques such as pre-bending of blades. This not only enhances aerodynamic performance but also ensures structural integrity during transportation and operation. Once the blades are manufactured, the transportation phase begins. In a groundbreaking operation, the blades are airlifted to their destination in Denmark for testing at their facilities. This involves careful coordination between technicians and engineers to ensure the safe loading and unloading of the blades onto the aircraft. The transportation process is not without its risks. The sheer size and weight of the blades, coupled with the precision required during loading and unloading, make it a challenging endeavor. However, through meticulous planning, simulation, and collaboration, the teams involved successfully navigate these challenges, ultimately achieving a successful outcome. Offshore wind energy projects rely heavily on the stability and reliability of their structures, particularly in the harsh conditions of the open sea. The offshore wind energy foundation jacket pile grippers and grout seals play crucial roles in ensuring the integrity and efficiency of these structures. Pile grippers are essential components that assist in leveling during the installation of jackets, the support structures for offshore wind turbines. They provide stability by securing the structure prior to and during the grouting operation, preventing movement between piles and sleeves. This not only improves the efficiency of the grouting process but also saves time and costs while enhancing the reliability of the connection. Moreover, in adverse weather conditions, pile grippers maintain the continuity of the piling process, ensuring operational continuity and safety. With capacities reaching up to 4,500 tons and diameters of up to 144 inches, these grippers are designed to meet the demands of offshore installations, with custom-built options available for specific requirements. In addition to pile grippers, grout seals play a vital role in offshore construction, providing a reliable seal for grouting operations on platforms and wind turbine foundations. With a unique dual lip design, these seals effectively prevent grout leakage, ensuring the structural integrity of the installation. Available in various diameters ranging from 600 mm to 3,650 mm, and optionally equipped with mud wipers to prevent mud penetration, these seals are tailored to meet the specific requirements of offshore projects. Together, these components contribute to the stability, efficiency, and reliability of offshore wind energy structures, ensuring their long-term performance in challenging marine environments. Offshore wind farm construction represents a remarkable feat of engineering and collaboration, exemplified by projects like Moray East, Scotland's largest wind farm. With the final installation of the V164-9.5 megawatts turbine in September 2021, the Moray East project reached a significant milestone, marking the culmination of years of meticulous planning and execution. Led by Vestas, in collaboration with Ocean Winds and partners such as Fred Olsen Wind Carrier, the Moray East project stands as a testament to the potential of renewable energy initiatives. The installation of 100 turbines underscores the scale and ambition of this endeavor, as it seeks to harness the abundant wind resources off the coast of Scotland. Scheduled for full commissioning in 2022, Moray East is poised to make a substantial contribution to Scotland's renewable energy targets. Once operational, the wind farm is projected to generate enough clean electricity to power approximately 950,000 UK homes, significantly reducing carbon emissions and advancing the transition towards a sustainable energy future. The construction process for Moray East involved a series of intricate steps, beginning with meticulous site selection and planning. Extensive environmental assessments were conducted to ensure compliance with regulatory standards and minimize ecological impact. Foundation installation, using monopile structures, provided stability for the turbines in the harsh marine environment, while turbine installation required specialized vessels and heavy lift cranes to transport and install the V164-9.5 megawatts turbines. Interconnection and cabling were essential components of the construction process, facilitating the transmission of electricity from offshore turbines to onshore grid connections. This involved the laying of high-voltage cables on the seabed and the deployment of submarine cables to transport electricity efficiently and reliably. Throughout the construction phase, a strong emphasis was placed on safety, innovation, and environmental stewardship. Collaboration among stakeholders, including developers, contractors, regulatory agencies, and local communities, was instrumental in overcoming challenges and ensuring the project's success. As Moray East prepares to join the ranks of operational offshore wind farms, it serves as a beacon of hope for the renewable energy sector. By harnessing the power of wind resources, projects like Moray East demonstrate the potential to drive meaningful change and create a more sustainable future for generations to come. The Wudongda Hydropower project in China is a remarkable feat of engineering, embodying the nation's dedication to advancing clean and sustainable energy sources. Located on the Jinsha River, it is a key component of China's broader strategy for power transmission from the hydropower abundant regions of Guizhou, Yunnan, and Sichuan to the densely populated eastern areas. With an estimated cost of $18 billion, the project is owned by the state-run China Three Gorges Corp. (CTG), and represents the inaugural installment in a series of 4 cascade hydropower stations along the Jinsha River. China, already a global leader in hydropower, has significantly expanded its capacity, reaching nearly 380 gigawatts by the close of 2021, growing at an annual rate of 2.6%. Wudongda is distinguished by its substantial scale, boasting an installed capacity of 10.2 gigawatts, making it the 4th largest hydroelectric project in China and the 7th largest globally. As part of the Cascade project, which also includes Baihetan, Shiladu, and Shangjaba, Wudongda exemplifies China's commitment to harnessing its hydropower potential on an unprecedented scale. The project's technical prowess is evident in its 12 850-megawatt units, with 6 each supplied by Voith and GE Renewable Energy. Notably, when Wudongda achieved full commercial operation in the summer of 2021, its 850 megawatt Francis-type turbines stood as the largest single units in operation at any hydro plant globally. The collaboration between Voith Hydro and GE Renewable Energy played a pivotal role in the project's success, addressing challenges across engineering, manufacturing, logistics, erection, and commissioning over a rigorous 5.5-year timeline. The project's completion signifies a significant milestone for China, solidifying hydropower as a cornerstone of its future energy landscape and a key contributor to the nation's environmental and sustainability goals. The hydropower generator operates by harnessing the kinetic energy of water to generate electricity, with impressive statistics underscoring its potential impact. Currently, the installed global hydropower potential is estimated at 4 million gigawatt-hours (GWH) annually, yet there remains an untapped potential of a staggering 16 million gigawatt-hours per year. At the forefront of this technology is Voith, a leading hydropower solutions provider with a vast international network. Their generators play a pivotal role in the hydropower generation process, where water's kinetic energy is transformed into electrical power. To put this into perspective, the Shiluodu power plant in China features some of the world's most powerful synchronous generators, boasting a maximum output of 855.6 megavolt amperes (MVA) at 125 rotations per minute (RPM). Furthermore, the Wudongda power plant surpasses even these figures, with generators reaching a remarkable 944.5 MVA at 90.9 revolutions per minute. The intricate design of these generators takes into account several crucial factors. Operational temperatures must align with material limits, ensuring longevity and reliability. The moment of inertia is carefully calculated within the stator bore dimensions to enhance grid stability, extend the time until the power unit reaches runaway speed, reduce water hammer pressure, and guarantee effective turbine regulation at shutdown. Voith's generators, designed with the latest state-of-the-art technology, undergo vacuum pressure impregnation (VPI) for stator bars and coils, ensuring reliability with rated voltages of up to 25 kilovolts (kV). Beyond initial installation, Voith offers comprehensive service and modernization solutions, exemplified by projects such as the pumped storage plant in Weir, Germany. Through modernization efforts, Voith increased the efficiency and reliability of the generators, contributing to the plant's re-establishment as the pumped storage power plant with the highest power output globally. Rotor and stator repair operations are integral for sustaining the functionality and longevity of generators, especially within power plants. Rotor rewinding is a crucial procedure to counteract wear on rotor windings, maintaining electrical integrity. J-strap and main lead replacement or reconditioning ensure efficient electrical conductivity by addressing damage or wear through careful examination and component replacement. Spacer block repairs are essential for rectifying misalignment issues, involving realignment or replacement of damaged spacer blocks to restore proper spacing. Amortisseur assembly repairs stabilize the rotor during operation, requiring the replacement of damaged parts or modification for enhanced stability. Collector ring machining and replacement maintain efficient electrical contact, using machining to smooth imperfections or replacing rings when necessary. High-speed balancing minimizes vibrations, reducing wear on bearings through weight distribution adjustments. Stator repair operations include rewinding to address wear on stator windings and maintain electrical integrity. Stator roux edges with modified ripple spring designs optimize the wedging system for improved performance. Addressing loose-end winding hardware ensures stability, and stator electrical testing verifies performance. Cleaning, Inspecting and testing hydrogen seal assemblies ensures their effectiveness in preventing gas leakage. In stark contrast to conventional hydropower methods that necessitate large and costly dams, Turbulent's technology showcases a revolutionary approach. Steering away from the expensive overland energy transport lines associated with dams, the innovation is inspired by nature, reflecting a commitment to sustainability and community well-being. Installation is a straightforward process, requiring minimal construction efforts. Excavating an area adjacent to the watercourse, incorporating prefabricated elements, and submerging the turbine's core into the basin constitute the primary steps. The opening of the partition to the river or canal triggers the turbine into continuous operation, harnessing energy efficiently. With a design that harnesses the power of a naturally occurring vortex, the turbulent turbine guarantees the safety of aquatic life. The low-pressure environment within the turbine ensures unimpeded fish passage, with the only wearing part being the generator, resulting in minimal downtime and maintenance requirements. A testament to its global potential, a 15 kilowatts demonstration system was successfully implemented in Chile. Operating with resilience against small debris and sand, turbulent turbines emerge as a viable solution for rural communities worldwide, capable of supplying energy to up to 60 households per turbine. Embrace the future of hydropower with Turbulent, an embodiment of decentralized, nature-inspired innovation. Coil winding. Transformer windings are designed to meet three fundamental requirements, viz. Mechanical, thermal, and electrical. They are cylindrical in shape and are assembled concentrically. Paper-insulated conductors of high conductivity and soft-drawn electrolytic-grade copper is used, which comply with international standards. Windings are made with great care by well-experienced skilled disc winding workers in dust-free and temperature-controlled environment. The most significant material in a transformer is the core. High-quality cold-rolled grain-oriented magnetic silicon steel should be used to ensure optimum losses and most efficient working of the transformer. The type of magnetic steel is chosen according to the desired loss level. The laminations are cut geometrically to ensure optimum flow of magnetic flux and minimum air gap between the joint of two consecutive sheets. The core is designed with safe flux density to minimize core loss and magnetizing current. The laminations are handled with utmost care to preserve magnetic properties. Coil design and quality are keys to transformer efficiency and longevity. Thermally upgraded paper should be used for longest insulation life. Coils are assembled with best insulating materials and are adequately clamped. The ends and tapping leads of all windings are connected by special extra flexible, insulated copper cables which are rigidly braced in position. Complete assembly of the remaining parts of the transformer. Finally, the transformer is transported to the construction site. Here it is installed and tested before being put into use. Here is Yorkville Sound's manufacturing facility located in Pickering, Ontario, Canada, a suburb of Toronto. Founded in 1963, Yorkville Sound is the manufacturer of Yorkville-branded PA loudspeakers and electronics, Trainer instrument amplifiers, VTC Pro audio touring systems, accessories and hardware. Upon entering the woodshop, one is immediately greeted by the sight of large slabs of timber, each waiting to be transformed. These machines are the silent artists, carving wood components used in solid plywood cabinet construction with meticulous precision. The commitment to resource optimization is evident, with CNC programs designed to maximize the use of every raw sheet. Venturing further, the cabinet assembly area is a symphony of coordination and precision. Here, pieces sculpted in the woodshop are assembled into speaker cabinets. Precision jigs, high tensile glue, and brad nails work in unison to ensure perfect alignment and stability. The workflow is a well-choreographed dance, with two parallel lines operating to maximize efficiency through this production phase. While 15mm Baltic birch plywood is a staple for its ruggedness and reliability, select products feature poplar or fir della, catering to preferences for a lighter, more resonant cabinet design. The meticulous attention to detail is palpable, with every imperfection addressed and every surface sanded and sealed before painting. The journey of each cabinet continues through automated overhead conveyors to one of the 4 in-house paint booths. Whether it's a rugged ultra-thin painted finish or a black rubberized epoxy coating, each cabinet is hand-painted by highly skilled technicians, allowing for careful attention to detail and a final inspection before final production. The commitment to environmental sensitivity is commendable, with the use of eco-friendly materials and advanced paint booths designed to recover all overspray. Finally, the painted cabinets move to their final destination, the finishing line, where they are completed with the installation of speaker components and other finishing touches. One of the standout features is Yorkville's in-house manufacturing of all essential metal components for their products. A visit to their metal shop offers a captivating view of where amplifier chassis, speaker grills, powered speaker amp bodies, and other crucial materials come to life. The shop boasts state-of-the-art machinery, including several computer-controlled presses and punches. It's fascinating to watch a chassis for one of their latest bass heads evolve. What starts as a flat metal sheet, meticulously cut and punched by their advanced machinery, is then skillfully hand-bent into its final form. Another intriguing process is the shaping of their custom perforated speaker grill material. The sight of completed, elegantly curved grills, ready for installation, is a testament to their attention to detail. To enhance durability and prevent rust, these metal components undergo a powder coating process. This method, distinct from the traditional wood cabinet painting, is executed in a dedicated, eco-friendly section of their facility. The variety of powder coat colors, textures, and finishes cater to the diverse product lines and brands birthed in their Pickering factory. Beyond the larger components, The metal shop's efficiency shines in the rapid fabrication of smaller precision parts, such as badges and control panels. They even manage their chassis screening and color inkjet printing in-house, further optimizing their production speed. Continuing the exploration, the next stop is the sector of the factory dedicated to crafting the vital electronic components of the products. Witnessing the newly acquired SMT machine meticulously installing small surface mount parts on one of the high-tech digital amplifiers is a spectacle of precision and technology. The design process here is robust, incorporating proven, rugged, and reliable through-hole parts, large ICs, film capacitors, and ceramic resistors, all requiring specialized auto-insertion technology. Observing the larger through-hole parts and ICs being integrated into a circuit board by one of the auto-insertion machines in the printed circuit board assembly area is a testament to Yorkville's commitment to quality and precision. The more intricate components are manually added by highly skilled technicians in the electronics assembly area, where elements like LEDs, switches, inductors, and capacitors are meticulously added to the boards, and any necessary point-to-point wiring is executed with precision. The sight of larger components like tube sockets and connectors being installed and hand-soldered is a vivid display of craftsmanship and technical acumen. Witnessing the finished circuit boards, ready for the final wave solder process, is a clear indication of the meticulous journey each component undergoes. This RoHS-compliant process seals the boards and solidifies all the electrical connections in mere seconds, leaving them ready for testing and inspection before being integrated into the chassis and cabinets previously observed in the metal shop. The convergence of the completed printed circuit boards and the meticulously fabricated metal chassis in the wiring line is where the product truly begins to manifest its final form. Here, printed circuit boards from the electronics assembly merge seamlessly with metal facades crafted in the metal workshop. A range of sophisticated products, from amplifiers and mixers to specialized electronic subassemblies tailored for powered speakers, and even guitar and bass combo amplifiers. The dedication to perfection is evident, with meticulous attention at every assembly juncture. Notably, several finished amplifier subassemblies stand ready for integration into powered speaker cabinets. Each unit undergoes rigorous testing, ensuring every component aligns with design expectations. Any anomalies prompt immediate rectifications, be it minor tweaks or circuit board adjustments. Post-assembly, products undergo a 24-hour burn-in, reinforcing their reliability. The heart of the factory lies in its finishing and final assembly area. This expansive section, spanning a massive 150,000 square feet in Pickering, is a hive of activity. Three distinct assembly lines work in tandem, meticulously crafting PA speakers, subwoofers, and even guitar and bass cabinets. The attention to detail is palpable, from the hand-affixed coverings on the Elite and YX loudspeaker products to the intricate assembly of Powerline Series ABS cabinets. Each station along the lines has a specific role, from installing internal bracing and crossovers to attaching handles and grills. Quality is paramount. Every product undergoes rigorous visual inspections and, ultimately, a comprehensive QC check. Here, a dedicated technician subjects each piece to an audio precision test, ensuring it performs to design specifications. Only after passing this stringent process does a product receive its serial number, ready for packaging and shipping. Ensuring the product reaches customers in pristine condition, regardless of their global location, is a priority. The final journey begins in a climate-controlled warehouse, ready for dispatch. Behind these products is Yorkville's adept engineering team, based in Pickering. Their state-of-the-art labs, equipped with the latest CAD and bench test equipment, are where innovations come to life, from tube amplifiers to LED lighting. This end-to-end in-house approach is truly commendable. We're in the repair facility of Global Electronic Services, USA. The company's expert is repairing an electric motor. After disassembled, the stator is cutted by a special coil cutoff saw. This helped to remove one end of the stator windings so that after burn-off the winding can be easily removed from the coils. Then it is burned on the burn-off oven at high temperature. Varnish and insulation are burned off and easier to remove the old windings without damaging the lamination slots. The winding technician records data including number of slots, how many coil turns, pitch and size of the wire needed to make coils and rewind the motor. The media blaster is used to remove the leftover varnish insulation and any contaminants. It uses a soft walnut shell to prevent any damage to the laminations but still removes any debris. After that, the stator and all the pieces of the disassembled motor are brought to a specialized machine that will steam clean and wash the parts, removing any debris or other contaminants. In the next step, insulation added to the lamination slots. An insulation paint is painted inside the stator and liner insulation is carefully measured and installed within the stator slots to keep the coils from making contact with the stator core. The winder forms coils using the data taken earlier. Technician will need 48 coils in 12 groups of 4. The coils are then added to the stator slots and grouped according to the motor's configuration. After the coils are in place, wedging is added to prevent rotor to winding contact and to further insulate. Then the winder technician adds lacing to add strength and stability to the newly formed windings. The stator is heated to 90 to 120 to remove any internal moisture and improve varnish bonding to the coils. It is then dipped in a special varnish treatment. The varnish bonds the windings together and prevents the coil movement within the stator core. Dynamic balancing. The technician will balance and calibrate the motor. In the reassembly step, the newly balanced rotor is installed first and then the bearings. Finally, the motor will undergo dynamometer testing and painting. Nestled in Sheffield, United Kingdom, the Witnessing Preformed Windings facility stands as a testament to nearly 5 decades of coil manufacturing proficiency since its establishment in 1968, now under the stewardship of the CBC Group. The facility's investment of over £2 million has not only fortified its capabilities but also ushered in a new era of cutting-edge manufacturing. The seamless orchestration begins with looping, where advanced machines effortlessly handle copper to produce coils with astonishing lengths of up to 29 feet. These looping machines, with their capability to handle extensive winding requirements, set the stage for what unfolds next. The shaping process, executed on automatic machines, captivates with its meticulousness. At various production stages, the coils are scrutinized to ensure uniformity in size and fit. The implementation of a new forming machine, storing coil shapes in internal memory, is a technological marvel, enabling the rapid production of identical shapes and sizes. This attention to detail extends to insulation systems, ranging from hot-pressed resin-rich to vacuum pressure impregnation, ensuring tight deadlines are met without compromising international standards. Quality assurance is a hallmark of the process, encompassing earth testing, tan delta, inter-turn, and partial discharge tests. The coils, designed with precision, are meticulously packaged and transported to clients worldwide. In this part, we'll delve into the key stages of speaker production at CIARE in Italy. The process begins with the magnet assembly. This component plays a crucial role in the speaker's function, creating the magnetic field necessary for sound generation. High-quality magnets are carefully selected and aligned to ensure optimum performance. The speaker cone is the part that physically moves to produce sound. It is typically made from materials like paper, polypropylene, or other composites. The cone's size, shape, and material are engineered to produce specific frequency responses and sound characteristics. The surround is the flexible ring that attaches the cone to the speaker's frame. It allows the cone to move while maintaining a proper seal. Surrounds are molded to precise specifications to ensure optimal performance and durability. Proper adhesion between the cone and surround is critical. This step involves the careful application of adhesive to create a strong bond that can withstand the forces generated during speaker operation. Free suspension control involves testing the speaker's suspension system, which includes the cone, surround, and spider, a component that helps center the voice coil. Lead wires are attached to the speaker's voice coil, which is responsible for converting electrical signals into sound. These wires must be installed precisely to ensure a secure electrical connection. Waterproof coating. To protect the speaker from moisture and environmental factors, a waterproof coating is applied. This coating helps prolong the speaker's lifespan and maintain its performance, especially in outdoor or high humidity environments. Titanium molding. In some cases, titanium is used for components like diaphragms or tweeter domes. Titanium is known for its lightweight and high-strength properties, which can improve the speaker's overall performance, particularly in high-frequency applications. HF, high-frequency, production. High-frequency components, such as tweeters or compression drivers, are designed and produced separately. These components are engineered to reproduce treble and high-frequency sounds accurately. LF, low-frequency, production. Low-frequency components, often referred to as woofers, are designed to handle the lower range of frequencies. These are larger and more robust components designed to move larger volumes of air. "100% quality control." Quality control is integrated into every stage of the manufacturing process. Before a speaker leaves the production line, it undergoes rigorous testing and inspection to ensure that it meets the manufacturer's exacting standards for sound quality and durability. Kingston Technology, a global leader in memory products, has set industry benchmarks with its meticulous manufacturing processes. With its headquarters in Fountain Valley, California, Kingston's commitment to quality and innovation is evident in its DRAM memory modules. Here's a deep dive into the manufacturing journey of these modules. Design and prototyping. Every Kingston DRAM module starts its life in the CAD room. Here, engineers design each layer of the printed circuit board, PCB. Once the design is finalized, a prototype is created and sent to compatibility testing labs. These labs ensure that the memory modules are compatible with various motherboards and systems they're designed for. The surface mount technology, SMT, lines are the heart of Kingston's assembly process. SMT is a method where components are mounted directly onto the surface of printed circuit boards, PCBs. This contrasts with older through-hole technology where components were mounted by inserting pins into holes on the PCB. SMT allows for more compact and efficient designs, making it the preferred choice for modern electronics. Screen printing. The SMT process in Kingston's manufacturing begins with the screen printer. This machine applies solder paste onto specific areas of the PCB where components will be placed. The solder paste is crucial as it will later melt to form solid solder joints, securing the components to the board. Automated optical inspection, AOI. After the solder paste application, the PCBs undergo an automated optical inspection. This step ensures that the solder paste is correctly applied in terms of quantity, position, and integrity. Component placement. With the PCB prepared, it moves to the surface mounting machines. The first machine places passive components like resistors, capacitors, and inductors. Following this, another machine places primary components, such as the DRAM chips. These machines are incredibly precise, ensuring each component is accurately positioned. Reflow soldering. Once all components are placed, the PCBs are sent through a reflow oven. Here, they are subjected to a controlled temperature profile, peaking at around 500 degrees Fahrenheit, 260 degrees Celsius. This process causes the solder paste to melt and then solidify, forming strong solder joints between the components and the PCB. Post-reflow inspection. After exiting the reflow oven, another round of AOI ensures that all solder joints are intact and free of defects. Rigorous testing. What sets Kingston apart is its exhaustive testing process. The company has developed and patented a range of testing equipment capable of testing hundreds to thousands of modules per hour. Additionally, server-grade memory modules undergo burn-in testing, simulating 3 months of intense server usage. This step is crucial to identify and eliminate any subpar memory cells. In the heart of Augsburg, Germany, lies the Fujitsu Digital Smart Factory, one of the world's most advanced IT production facilities. Let's delve into the intricate processes. The factory boasts an impressive daily capacity of producing 9,000 units of mainboards. Each of these mainboards begins its journey with a unique identification. The printed circuit board, PCB, is labeled with a distinct serial number. Surface Mount Technology, SMT, for the PCB. The SMT process for the lower side of the PCB involves 3 crucial steps. Screen printing. This is the initial phase where solder paste is applied to the board. It ensures that the components will adhere correctly during the soldering process. Pick and place components. Precision is key. Automated machines meticulously pick and place the required components onto the PCB. Reflow soldering. The PCB is then passed through a reflow oven, where the solder paste melts and solidifies, ensuring the components are firmly attached to the board. For the upper side of the PCB, the process is slightly abbreviated but equally rigorous. Screen printing. Similar to the lower side, solder paste is applied to ensure component adherence. Pick and place components. Once again, machines with pinpoint accuracy place the components onto the PCB. Human-robot collaboration, the future of manufacturing. A significant highlight of the Fujitsu facility in Augsburg is the groundbreaking collaboration between humans and robots. In partnership with automation leader KUKA, Fujitsu has integrated robots that work hand-in-hand with human colleagues. These robots are equipped with sensors that detect the proximity of humans, adjusting their speed to ensure safety. The robots are trained by humans through manual guidance, with machine learning embedding each step into the robot's operations. Through hole technology, THT, process. THT is another essential process in mainboard production. It involves automated insertion of THT components. Machines are employed to insert components that require through-hole mounting. Manual insertion of THT components. Some components, due to their complexity or specificity, are inserted manually by skilled technicians. Wave soldering under nitrogen atmosphere. This process ensures a robust connection of the components. The use of a nitrogen atmosphere minimizes oxidation during soldering, ensuring a clean and strong bond. Quality assurance and testing. Once the mainboards are assembled, they undergo rigorous testing. Visual inspection. An automated optical inspection is conducted on 100% of the units. This ensures that there are no visible defects or issues with the mainboards. Electrical test. Every mainboard undergoes a 100% in-circuit test, ICT. This ensures that the board functions electrically as intended. Final function test. Before leaving the factory, each mainboard is subjected to a 100% functional test, ensuring that it meets the high standards set by Fujitsu. The advancement of biaxial rotor blade testing methodologies is pivotal in enhancing the realism of test loads. By integrating novel approaches, such as combining fatigue tests in both flapwise and edgewise directions, we aim to streamline testing procedures while also achieving more authentic load representations. This not only optimizes testing duration but crucially enhances the accuracy of load simulations, aligning closely with certification targets. In pursuit of innovative testing methodologies, virtual testing techniques play a complementary role, augmenting the insights gained from physical tests. By leveraging numerical simulations, the engineers can forecast blade loads, deflections, and excitation forces with greater precision, particularly valuable in biaxial testing scenarios. The complexity of the test setups necessitates meticulous planning and execution. Utilizing components like glass fiber springs and decoupled meshes to fine-tune system eigenfrequencies underscores the intricacies involved. Drawing from over 3 decades of experience, including numerous commercial blade certification tests, engineers continually refine our methodologies to uphold the reliability of wind turbine blades throughout their operational lifespan. The actual chip production takes place in a fabrication area, commonly referred to as a fab. Micron's fabs are state-of-the-art clean rooms, boasting an environment that's 100 times cleaner than a hospital operating room. This ensures that the pure silicon wafers, which individual memory chips or die are built upon, remain uncontaminated. Photolithography, a key step in the fab, involves coating wafers with a photoresistant material. Circuit patterns are then exposed, resulting in ultra-fine pathways on the wafer. Advanced robotics shepherd these wafers through a myriad of processes, a journey that spans weeks. Before assembly, the crucial probe step comes into play. Each die on the wafer undergoes an initial functionality test using a probe card equipped with tiny needles. This card interfaces with each die, transmitting and receiving test data. This step is vital as it identifies and filters out any defective dies, ensuring only the best proceed to the assembly phase. In assembly phase, wafers are first thinned and adhered to an adhesive backing for stability. Using a precise diamond-edged saw, the wafer is diced into individual dies. Guided by the wafer map from the probe step, qualified dies are selected and placed onto circuit boards. Solid gold wires connect each chip to the board, ensuring optimal conductivity. Each die is then encapsulated in a protective plastic mold, safeguarding it from environmental factors, before proceeding to further testing. Every memory chip is subjected to rigorous testing to uphold unparalleled quality standards. Utilizing specialized equipment, these chips face extreme conditions, ensuring only the robust components make their way to consumers. Beyond just functionality, Micron ensures each chip not only meets but often surpasses its designated performance benchmarks. Once these stringent tests are passed, chips are distinctly laser engraved with identification markers, ensuring traceability and authenticity. A meticulous optical scan further ensures that each chip adheres to exacting fit and form criteria. Safety and quality don't end at the chip level. These chips are securely housed in industry-standard anti-static packaging, safeguarding them from potential hazards. Many of these high-quality chips find their purpose in memory modules and solid-state drives. Leveraging state-of-the-art assembly machinery, chips are seamlessly integrated onto circuit boards. Before these products reach customers, they undergo one final round of exhaustive testing. The construction of the Binh 1 wind power project reflects a significant step towards sustainable energy development in Vietnam. Covering an expansive area of 27.7 hectares, the wind power plant boasts a substantial capacity of 80 megawatts, generating an annual electricity output of 280,000 megawatt-hours. The total investment for this venture amounts to approximately $158 million United States dollars. The wind farm comprises 26 wind turbine towers, each with a capacity ranging from 3.0 to 3.3 megawatts per turbine, and towering over 140 meters in height. The strategic location of the project facilitates the integration of wind energy into the national grid through the 220 kV CIARE Back-Lu 2 transmission line. This initiative not only contributes to the national power grid but also aligns with sustainable practices by combining wind energy production with aquaculture to enhance land utilization efficiency. The socio-economic impact of the Binh 1 wind power project is noteworthy. Beyond creating stable employment opportunities for the local population, it contributes over $3.4 million United States dollars annually to the local budget. Furthermore, the project plays a pivotal role in the economic restructuring of the region, influencing Back-Lu province and the surrounding areas positively. The second phase of the Binh 1 wind power project strategically utilizes the existing infrastructure of its predecessor to optimize the use of land and minimize environmental impact. Situated along the coast of Binh A and Vinh Hao communes, the project covers an expansive area of approximately 935 hectares. The Binh 2 wind power project introduces a unique element by installing wind turbines in the sea area of Vinh Tin commune, occupying a sea area of about 1,119 hectares. This innovative placement reflects a commitment to exploring diverse solutions for renewable energy generation while considering environmental sustainability. The combined investment for both projects totals $223 million United States dollars. The anticipated electricity generation from these projects is estimated to be around 400 gigawatt hours, generating an annual turnover of $34 million United States dollars. China's dominance in the tablet manufacturing and assembly industry is indisputable, with its Android tablet factories serving as prime examples of efficiency and scale. In this part, we will delve into the specifics of this thriving industry, focusing on a typical Android tablet factory in China, and emphasize the key statistics and numbers that define and drive this sector. China's leading position in the tablet manufacturing and assembly industry is substantiated by robust numerical data. Chinese manufacturers consistently command over 40% of the global tablet market share. In the year 2020 alone, Chinese tablet manufacturers collectively produced an impressive total of approximately 152 million tablets, as reported by the International Data Corporation, IDC. This monumental production output underscores China's significance in the global tablet industry. Now, let's delve deeper into the specific numerical aspects that shape the operations within a typical Android tablet factory in China. A typical Android tablet factory in China boasts an extensive workforce, often consisting of thousands of highly skilled and dedicated employees. For instance, Foxconn, one of the world's largest electronics manufacturers with numerous tablet production facilities in China, employed a staggering workforce of approximately 1.3 million employees in 2020. These skilled workers play a pivotal role in the efficient production of Android tablets. The hallmark of a typical Android tablet factory in China is its remarkable daily production capacity. These factories can produce an impressive range of tablets daily, with output rates ranging from 20,000 to 100,000 tablets per day. The actual capacity depends on factors such as the size of the facility and its production capabilities. Component sourcing. Android tablet factories in China maintain a robust network of component suppliers to meet their production needs. The electronics component market in China is vast and diverse, with over 2,000 electronic component manufacturers as of 2021. This extensive network ensures a steady supply of essential components required for tablet assembly. A typical Android tablet factory in China operates multiple production lines dedicated to printed circuit board (PCB) assembly. These production lines can efficiently assemble hundreds of PCBs per hour, showcasing the precision and scale of tablet manufacturing operations. Quality control is a paramount aspect of tablet manufacturing in China. These factories adhere to stringent quality control standards, with a focus on achieving very low defect rates. The industry norm often demands defect rates of less than 0.5%, ensuring a consistently high level of product quality. China's Android tablet factories are responsible for the exportation of millions of tablets to international markets annually. As of 2020, China's tablet exports surpassed the 100 million mark, as reported by the General Administration of Customs of the People's Republic of China. This extensive export volume highlights the global reach and influence of Chinese tablet manufacturers. Key factors driving China's success in tablet manufacturing. China's success in tablet manufacturing is driven by several pivotal factors, each supported by noteworthy figures. Cost-effective labor. China's competitive edge is significantly bolstered by its relatively low labor costs. In 2020, the average monthly factory wage for manufacturing workers in China averaged around $650. This figure is notably lower than wage levels in many other countries, enhancing China's attractiveness as a manufacturing hub. Infrastructure. China's extensive network of ports and shipping routes plays a crucial role in facilitating the importation of raw materials and the exportation of finished tablets. With 34 coastal and inland ports, China efficiently handles vast amounts of cargo annually, supporting its manufacturing industry. China boasts a well-developed transportation infrastructure, featuring over 160,000 kilometers of railways and an extensive highway network. This infrastructure enables the seamless movement of goods within the country, further enhancing manufacturing efficiency. Skilled workforce. China consistently produces a substantial number of engineering and technical graduates each year, with an estimated figure of over 4.7 million science and engineering graduates in 2020. This pool of skilled talent reinforces the technical expertise required for electronics manufacturing. Supply chain efficiency. China's vast ecosystem of component suppliers ensures a stable and efficient supply chain. For example, the presence of over 200 silicon wafer fabs in China caters to the semiconductor needs of various industries, including tablet manufacturing. Technological advancements. China's commitment to automation is evident in its deployment of industrial robots. In 2020, China boasted an astounding number of over 1.4 million industrial robots in operation, claiming the highest count globally. This automation fosters efficiency and precision in manufacturing processes.